चैनल है Hi, can you hear me?
Yes, sir.
Okay. Okay, I hope you can see my screen also, as well as what I'm writing on the board. Okay, so I think we can start because we're already at 4 o'clock. So it was good to see that many of you have uploaded very nice constructed own problems and uploaded them to the Google Drive. So keep doing that. And as and how you develop your collection of problems, I would also suggest at some point you can start to categorize them in some way that everybody may construct many problems, but in your mind that some problems have been really well designed and some maybe not that well designed. So start to sort them in that way. And like, what if you were to pick some 3 or 4 problems which really you find that these are really good ideas? Because what could be the criteria to select a good problem? I think as a problem setter, you may have some ideas in your mind. So I think one thing which is important is, does that problem teach you something, or anybody who is going to solve that problem, does it illustrate some nice problem solving idea or technique, like how to use a particular theorem, how to use a particular property? If there is any useful insight like that which a problem will bring out, then that is a really good problem actually. So if you have some out of all the problems you are creating, some 2 or 3 problems or even more depending on your selection, which you find really to be something which others will like to look at. So you can try to segregate your problems that way, and so everybody else can also look at your problems. I'll encourage you to do this anyway. So everybody, you can go to Google Drive and look at each other's uploaded problems and try to solve them. Try to find new solutions of your own. I think some students have uploaded only the problems, which is fine. I guess everybody has their own style. Somebody can also do something like this, that for every problem you also upload 1 or 2 lines of a hint, maybe if like somebody wants to try out the problem before they actually look at the solution, so they can do that. Or somebody wants to upload a full solution, so you can do all of these things and develop a really good collection of problems over time. Okay, so I'm going through the problems. I didn't get chance to solve all of them so far, but I'll keep trying on my own. So as and how I solve the problems, I'll give you some feedback. But so far the problems uploaded are of really good quality. So really good that everybody's trying. And see, the important thing is trying. You may not feel that your problem is very good or there is room for improvement. That always happens. Even with problems which I create, there is always something later on which occurs to me that, okay, maybe I could have done this, I could have done that. That is fine. But as you're trying, you're developing some important observation skills, that what goes into the construction of a good problem. Because if you internalize that logic, that will help you to solve new problems in exam or anywhere you want to do. So keep doing that. Okay. Then apart from that, I hope all of you are able to watch the YouTube video for the power of a point and able to follow the theory from there. So I would like to give this a try for a few weeks, that we keep on sharing the theory part through some like videos like this, so that you have something to do in the middle of the week as well, right? And so that we get a chance to discuss some particular aspects. Sometimes actually what happens, I record that video, but later on I realize that I should have added 1 or 2 points here or there, which I forget to do at the moment. So those things we can discuss in the Sunday lectures, as well as some problems. So that is how we can try to construct this discussion. So beginning with what I generally talked about, of course, power of a point. So I think everybody knows the basics of the power of point, the basic theorem, which is the fact that when you have two chords in a circle, the product of the segments, the PA into PB is PC into PD. So that was the basic idea of the power of a point, right? Actually, one thing which I didn't forgot to mention in the video is the fact that the power theorem is of course useful, but what is even more useful often in problems is the converse, right? So you may already have some experience with this, that if you have 4 points which satisfy the given condition, then from that you can conclude that the 4 points are concyclic. So actually the converse is just as important as the main theorem. So it's always that good to remember them together, the power as well as the converse. And you may also come across problems where the converse is important. Another aspect which I think I could have emphasized more is that, so when a point is outside the circle, so we already know that the this product that we know that PA into PB is PT square, right? So in that case, basically the tangent becomes the limiting case where both the points of the chord are basically overlapping. So that is why I get PA into PB is equal to PT square. But I mean, this is especially important because that gives one more way to characterize the power, right? So when the point is outside the circle, the power is just the square of the tangent length. And we can see some examples of how this can be useful. For example, given this fact that the tangent square is the power. So can we think of some way of constructing the radical axis of two circles using this property? So if I have two circles, how can I construct the radical axis? So what is the radical axis? It is the set of all points which have equal power with respect to both circles, right? So if I put that in terms of the tangency, what does that mean?
The locus of all points through which if we draw tangents to both circles, they will be equal.
Yes, correct. So we are looking for all the points from where the lengths of the tangent segments will be equal to both the circles. And if you have watched the video, you already know that in most cases the radical axis is going to be a straight line, right? And so to characterize that straight line, it's enough to look at 2 points, or actually even 1 point, because we know that radical axis is also perpendicular to the line joining the centers. So can we find this 1 point from where the tangents will be equal to both these circles?
Sir, we can draw common tangent to two circle and then we will find the midpoint of that. So it
Right.
will be 1 point.
Yes, correct. Okay, does everybody follow what Om is saying? That if I draw the tangent, common tangent to both circles, then this segment, the midpoint of this segment, right? So that will have equal, the tangent from this point will be equal to both the circles. So this point has to lie on the radical axis. And in fact, the question is that we have multiples of tangents, right? In general, we have 4 possible tangents that you can draw between two circles. So you see the natural sort of corollary here is that all the 4 tangents, if you consider any, like for example, this is a direct common tangent. You could also consider the indirect common tangent like this, and its midpoint. So in fact, all those 4 midpoints of those tangents are all going to lie on the radical axis. Okay, so this is a very nice way of constructing the radical axis of two circles. Only caveat is, I mean, do you see a situation where this approach cannot work?
Sir, concentric circles.
Right. I mean, not just concentric, like if one circle is inside another circle. Actually, for concentric circles, you may have noticed that the radical axis cannot be defined. So it's actually the empty set, right? So if the two circles are concentric and distinct, then the radical axis is the empty set. But if even for non-concentric circles, which is one inside the other, there is no concept of a tangent that we can define. So for this situation, we have to come up with a different construction of radical axis. So has anybody got a chance to think about and suggest a way to construct radical axis for any two circles, not just inside the other, but how do we construct radical axis in general? So for that, the most important property.
An arbitrary circle passing through the two circles, and then the radical axis of that arbitrary circle and the two circles each, and we know that the
Right.
3 radical axes are concurrent. So then we can draw
Yes.
the perpendicular.
Right, correct. Okay, so we are using the fact that if we have any three circles, their pairwise radical axes are going to be concurrent. Okay, so does everybody follow that? I actually don't remember whether I covered the proof of this or not, but I think it's fairly easy to see, right? Because if I have, let's say, any three circles, and I take the radical axis of the first two circles and let them meet at some point P. Okay, so then by the definition, we know that P has equal power with respect to the first and third circle and the second and third circle. So it has to lie on the third radical axis. So the fact that the three radical axes are concurrent can be used to locate any arbitrary point on that radical axis, right? So what Janvi was explaining was that suppose so in this diagram, the black circles are the two given circles for which I want to construct the radical axis. So I construct a third, this blue circle is any arbitrary circle I've chosen. And because I want to construct a radical axis, and as you already noted that the common chord between intersecting circles is the radical axis. So, I would not choose any random circle, but choose the intersecting kind of circle. So if I choose one circle, I'll get 1 point on the radical axis. Now that is sufficient. From there, you can simply drop the perpendicular to the line joining the centers, or you can take one more blue circle, right? So you can take any number of blue circles you want, and all of those like resulting points will lie on the radical axis. Okay, so that is one way of doing this problem. Okay, actually there are few exercises that were suggested at the start of the section. So I don't know if you got a chance to go through them. So apart from that, yeah, one more thing maybe I'm curious to know. So you may have seen that we have discussed multiple solutions to the power theorem itself, right? Multiple proofs. One using Pythagoras theorem, one using coordinate geometry. Any other ideas which anybody, if you have thought about this problem, that how can we prove the power theorem itself?
Yes,
Any
I
other
have
way?
the proof by Stewart's theorem.
Proof by Schwartz theorem. Wow, interesting. Can you give us the brief outline that what are the main steps involved?
I've checked it for when P is inside the circle, but
Okay.
basically we applied the Stewart's theorem to triangle OAB, where OP is the segment.
Okay. Can you describe the diagram for us? So what should I draw?
So O is the center,
Okay.
AB is the chord, and
Okay.
P
And
is on like AB inside the circle,
okay.
and we apply Stewart's theorem to OP.
Okay.
As
In this
to
triangle OA.
OE. Yeah.
Okay. Okay. So then from that we can compute OP in terms of the other lengths. Okay.
We can directly compute PA into PB.
Oh yes. But in that you will get the lengths. In fact, let me write it out. It looks interesting to me, but I have some questions. So if we write OP square, you want to write OP square in terms of the length. So if I in your standard notation, let me call this point C. Let me just relabel the triangle, the point, so that we can apply the standard Stewart's theorem result more easily. Okay. So as per the one of the ways you can write it as, so these are small b, small c, small a, and if I call these segments M and L, so what Stewart's theorem says is that AL square, so the BC into AP square plus AMN is equal to, you have to multiply the opposite side. So B square gets multiplied by M. So MB square plus NC square. Okay. Now in this is the most general formulation. Now in that we know that B and C are the radii of the circle we are talking about. So we can replace B and C by small r. Okay, so let us call that small r. And so what we get is A times L square plus Mn is equal to R square times M plus N. Okay, so my question, everyone, is that how
Replace M
So
plus
here-
N by A and cancel it out.
we can replace M plus N by A. Okay,
Cancel it out both sides.
we can cancel it out. Oh yes, the correct. Yes. Oh, but this is very nice. So we actually get what we wanted. So and in fact, in the L the more commonly we have used the letter D instead of L. So I can do that. So I'll get D square plus Mn is equal to R square. And yeah, so I get Mn is equal to R square minus D square, which is exactly what we also obtained. Yeah, this is very nice. And I think so Stewart's theorem can be interpreted for the point P outside the chord BC also, but maybe some signs change because to take care of the directionality. But I am quite sure that a very similar proof can be applied there also. Yes. Okay, this is very nice. Anybody else? Any other approach that gives the power result? Maybe just keep thinking. Maybe something else will occur to us. Just like Pythagoras theorem, you already discovered a dozen proofs. These elementary building blocks often have multiple approaches. Actually, one thing is that you may know Pythagoras theorem proof using power theorem. You may have studied that, and we in the video I showed how to prove power theorem using Pythagoras. So there is a bit of a circular argument there. So depending on what is your starting point, you will typically in the theory of geometry, you'll do one theorem first and then use that theorem to prove the other theorem. So it is possible to have two different approaches to develop geometry. Somebody who does Pythagoras theorem first and then uses that to prove the power result, or somebody else could do the other way. So first prove the power theorem using something else and then use that to prove Pythagoras theorem. So both are equally effective. Okay. So so then coming to these problems, which or rather exercises, I would say. So if you plot these graphs, right? In particular, I'm interested to know whether this third and fourth question, how do you resolve? So the third one, where the circle is fixed with some radius, and I have given some real number k, and you have to find all the points for which that power is equal to k. So what will that set of points look like?
Sir, I solved the third one.
Okay.
So I got the answer as it would be a circle with center O, which is the center of the given circle, and
Okay.
radius should be root over R square plus K.
Right. And when will such a locus exist or not exist?
So it will not exist when R square plus K is less than equal to 0.
Yes, correct. Okay, so does everybody follow that? Basically, I'm saying that yes, go ahead.
I wasn't able to do the fourth one exactly. Like I reached halfway, but
Okay. Okay. So we'll first just revisit the third one. So I'm looking for the locus of all points P such that the power of P with respect to the circle. So this notation, as you may have seen, I've introduced that P subscript gamma, just to make it easier to write it again. So I want this power to be some value K. And so in terms of the formula, this means that D square minus R square is equal to K. And therefore that puts restrictions on because the circle is given, so small r is constant and k is constant. So this simply means that d square is equal to r square plus k. And so if naturally this r square plus k term is negative, then such a p cannot exist, right? So then the solution set is empty basically. Otherwise, it will be a circle whose radius is exactly root of r square plus k, right? So that is the radius. Right. One more interesting observation that you may have realized from the previous question. So suppose I have 2 points P and Q, okay, and I'm interested in the difference of the power. So the power of P with respect to the circle minus of the power of Q with respect to circle. If you write out those expressions, the radius of the circle cancels, right? So in fact, what you get is OP square minus R square minus OQ square minus R square. So because the radius cancels out, so you see the difference of the powers has no connection with the radius of the circle. So even if I increase the radius of my circle or decrease the radius of my circle, this difference doesn't change. So that is important to notice. Okay. Although if it does depend on the position of the center, right? So if I change the location of O, then these quantities may change. But if the center is the same, but the radius is different, then it makes no difference to the difference of the powers. Okay. So then coming to question 4. So question 4 was kind of reverse. So there the circle is not fixed, the point is fixed. So question 4 was that there is a point P and I've given again some real number K, and I'm looking for all the circles for which the power of P is K. So access the setup is exactly the same, right? Again, it's the same. There is some circle I have to locate. So in fact, I have to locate this pair of numbers, small d and small r, such that, so I have to find d and r such that d square minus r square is equal to k. Okay. So as such, for the most part, pretty much this means that, like if I write this equation as d square is equal to r square plus k, right? So now you can choose any value of r and that will give you a value of d, right? But so there are some restrictions there that depending on what is the value of k. So I think we can make two cases. So case one, k is positive, and case two, k is negative. In fact, we can say case one is k greater than or equal to 0. So we can handle these two cases separately because in depending on which case we are talking about, the calculation is slightly different. Okay, so if the case one where k is non-negative, so there it is guaranteed that, so in this equation d square is equal to r square plus k, we can choose any value of r, right? Any positive value of r is fine, but then that is enough to guarantee that the d can be well defined, right? So d will be equal to root of r square plus k. Okay. And so for that value of r, that particular value of d has to be chosen. And so if I were to draw the diagram of this case one, it will look something like this. So the point is here, k is positive. So going back to the tangency interpretation, can you see how I can draw such a circle? So for example, take the case of when the r is equal to 0. So when r is equal to 0, I'm talking about a point circle, a circle with 0 radius. So where will that be located in the plane?
Can you repeat?
So let us consider, because as I said, I can choose any value of r in this equation, right? So I'm saying, let us say r is equal to 0. So I'm talking about a point circle. Okay? So a point is also a circle actually of 0 radius. So where should that point be in the plane so that the power of P is k?
It should be at root k, right, sir?
It should be at root k, right? I mean, this equation only tells that when you put r equal to 0, you get d is equal to root k. So from P, if I draw a segment of length root k, and see that is why we needed k to be not negative, so that we can construct this segment of root k. And so that this point I can draw a circle of 0 radius, and so that can be a valid circle for which the power of P is k. Okay. But continuing now, suppose r is not 0, r is some positive value. So how can I draw such a circle? Suppose I give you the radius of r, let's say r is equal to 2 centimeters. Then how will you construct this circle? From this equation, we can compute the distance, right? So if I put 2 over here, I'll get d is equal to root of k plus 4. So I know that the center of my circle has to be at distance of k plus root of k plus 4 from P. But I'm asking if you can think of a different approach, that where will that circle lie? Yes, Raghav.
So then maybe we can draw a triangle with whose base lengths are r and root k, and then the hypotenuse
Yes.
would be d. And then
Exactly.
just that
In fact,
distance.
yes, correct, Raghav. And in fact, from that, do you see that in this diagram I already drawn the root k side of the triangle?
Yes, sir.
Yes. So actually, if you think about it, this the first point that we located, this black point, which is the circle of 0 radius. If I draw any circle like this, right, such that this same line segment is the tangent to that circle, do you see that it follows that for this green circle also the power of P is going to be k? Because the tangent segment is root k, so the power is the square of that. So you see, there's an infinite family of circles like this, all these circles which are tangent at the same point over here. And like you can keep going on like this. And in the other direction also, there's nothing special below the line. The same thing can be done above the line also.
But
So this entire
first infinite number of lines of length root k.
infinite number of lines of length. Lines.
Line segment.
What do we well? Line segments. Yes. Yeah. I mean, yeah, that is one more thing we have to add, that this we have done in the particular direction, but I can rotate the whole diagram. So it's like this entire family can be rotated around point P anywhere in any direction, right?
Yes.
So that is the additional degree of freedom. But suppose you fix that this is the point of tangency, then even in that we have an infinite family like this.
Yes.
Okay. And we are going to revisit this diagram in the next section. So when we do coaxial circles, this is exactly a family of what we call coaxial circles. So coaxial means they share the same axis. In this case, it's the radical axis. So this is a family of coaxial circles actually. So I mean, if you think about it, these problems, they may seem very trivial, but actually they are motivating the theory which is going to come next. So if you can spend your own time to understand what is the problem, what are the implications of that particular property, you might do the next topic on your own, which is very good. So if you can do the theory without my prompting, then you're already on your way to becoming a better student. Okay, so give it a thought. So this was the case of k greater than or equal to 0. In the case of k less than 0, you have to do slight changes, because now if you look at the equation d square is equal to r square plus k, now I don't have the freedom to choose any value of r, right? Because with that value of r, I cannot guarantee that the whole equation is going to become greater than 0. So I'll change my strategy a little bit. Instead of choosing r first, why don't I choose d first? So I can rewrite this as d square minus k is equal to r square. And now given that k is less than 0, which means minus k is positive, right? So do you see that this quantity is always going to be positive, no matter which d you choose? So now you have the freedom to choose any value of small d, and that will give you the value of r, right? So the diagram may look something like this. So you choose a point P, you choose any distance d that you want. So now you know that this is the center of your circle. And from now you have to draw the circle, and knowing that k less than 0, it means that that circle is going to be, the point P is going to be the interior of that circle. So now that, in fact, let me do this. Even before that, so the smallest value of d I could have chosen is 0, right? So if I choose the value of d as 0, then it means that I'm choosing P to be the center of that circle. And so what is the radius of that circle going to be? So the radius has to be root of minus k, right?
But so that is not real.
Yes.
That is real. Minus
K
k is
is
positive.
negative.
K is negative, right? So minus k is positive. Okay, so this is the first circle that we consider. And now as the value of d changes, the radius of the circle will keep on changing, and the circle will keep moving away from P. So actually, I have not plotted this family of circles, but I will encourage you to do that. That what does that family of circles look like? I'm imagining it is something like, basically what will keep on happening, right? That circle will keep on expanding in radius, while at the same time its center will keep moving away from the point P. So in the limiting case, do you see what will happen when the radius of the circle is very large? The diagram may start to look something like this. So because the product PA into PB that we're talking about, it will have to be something like this. The one edge of the circle will be very close to the point P, and the other edge will be very far. Only then that the product will be equal to some constant K, right? So it may be interesting to see as the value of d and r changes, how does this family look like? I think it looks something like this. So it will keep on, it will be another family of circles like this. These are not coaxial circles actually. I don't even know what these circles are. But yeah, it looks like an interesting different family of circles. And I wonder if they have any interesting properties that you will want to explore. Okay. But basically, this case 1 and case 2 will lead to some very different kinds of solutions, depending on whether k is positive or k is negative. And I mean, just think that all of this development was initiated by just the definition of the power, right? We didn't even look at multiple circles, like radical axis is not even required in this section. So even with that basic observations, you can do so many things. Okay. Now coming to the power with respect to multiple circles. So I'm sure you must have already watched the section about how we solved the first problem, the P of gamma 1 is equal to P of gamma 2. I'm curious if we have spent more time on the remaining problems, question 4 in particular. So there, how can you generalize this idea to multiple circles? And what do you think in general that power, that locus will be? So any observations related to that? Like for this, the equation which I have written here, k times P of gamma 1 plus L times P of gamma 2 is equal to some constant m. So what do you think this locus is going to be?
Sir, I got a circle.
Okay, you got a circle, but is it always a circle or you have to be somewhat careful? But
Sir,
you're
K
right in general.
plus K plus L
Yes.
shouldn't be 0.
Yes, correct. So if k plus L is 0, then it is not a circle, but otherwise it is always a circle. Okay. And so let us do the most general problem of this kind and see there are very interesting things that this leads to. Okay. So this is the setup, and I'm going to use coordinate geometry over here because again, I hope you observed the correlation between coordinate geometry and the power definition, right? So just to revise that fact, so when I'm talking about a circle with a center h comma k and radius r, so we know that the equation of that particular circle is x minus h square plus y minus k square minus r square is equal to 0. And so the observation was that this, if I look at it as a function of two variables, f of x and y, then in fact this function gives me the power of any point in the plane. So if I choose any point P whose coordinates are, let's say, x naught comma y naught, and I want to find the power of P with respect to this circle, I just have to substitute x naught and y naught in this expression, and that will give me the power of that point. And this follows from the fact that actually this quantity is nothing but d square, right? The distance of that point from the center of that circle. So therefore this quantity is actually d square minus r square. Okay. So we'll leverage this observation to the fullest extent in this problem. So let us say this is the setup. So I have given n circles. Okay. So those n circles each with their own radius. So let us say the circles, the centers are h1 comma k1, h2 comma k2, hn comma kn. Okay, so these are the n centers of those circles, and we have the n radii of the circle, and we are considering, we want to find the locus of all points such that the power of the point with respect to the first circle. So if I call these circles gamma 1, gamma 2 up to gamma n, then power with respect to gamma 1 plus power with respect to gamma 2 plus power with respect to gamma n. So these n power expressions, they will get multiplied with some constant, right? So if I call the constants maybe alpha 1, alpha 2 to alpha n. So alpha 1 times the first power plus alpha 2 times the second power, all the way up to the last one. This whole sum is some constant c. So I think this is the most general problem of this kind that you can imagine. If we have to give it some name, it is basically the most general, like linear combination of powers. So I would say locus of. So the locus of the linear combination of powers with respect to n circles. And if you think about it, if you solve this problem, then all the other problems are going to be special cases, right? With some suitable substitution of the values of all these alpha 1, alpha 2, you should be able to solve all the other problems, even question 5, right? Because question 5 also, if you see, it is actually, if I just take this to the other side, it is power of gamma 1 is equal to k times power of gamma 2. So that is also simply a linear combination of powers. Okay. So given this starting point and the coordinate geometry interpretation, you see we can directly write the equation that that power point has to satisfy. So if the point P has coordinate x comma y, then the equation is that alpha 1 times the first power, the x1 minus x minus h1 square plus y minus k1 square minus r1 square plus alpha 2 times etc. etc. So there will be n such terms all the way up to alpha n. This is equal to c. So this is simply an equation involving x and y, right? And so any point which satisfies this equation, that will be a valid point on the locus that we are looking for. So how do we see any way to simplify this? Seems like a complicated equation, but can we quickly regroup terms and make it simpler to digest?
We can write the coefficient of x square as alpha 1 plus alpha 2 plus dot dot plus alpha n, and similarly for y square.
Yes, correct. Right. So if you expand each bracket and regroup it, you see that x square will be multiplied by alpha 1, alpha 2, and alpha n, all of them. So I can directly write x square times, and I'll use the sigma alpha I. So this is, in the short form to say the sum of alpha 1, alpha 2 up to alpha n. Not sure if you have been introduced to this symbol, but it will help us to write the equations much more compactly. So sigma alpha I will multiply both x square and y square, correct? Then after that, there will be some linear terms, right? So what is the linear term going to be? What is the coefficient of x going to be?
Minus 2x into alpha 1 h1 alpha 2
Yes.
h2.
Right. So again, we will write it as sigma alpha alpha I h I. I'm using a bit of actually being lazy, you can say. Every time we write this sigma, we have to also write what is the range on which that index varies. So here alpha I, where I goes from 1 to n, but that range is going to be constant, the same for all our equations. So I'm just avoiding to write it, but it is understood, right? So in every case, the range is I going from 1 to n. Okay? So this is the coefficient of 2x, and similarly the coefficient of 2i will be same thing, right? Sigma alpha I ki, right? And then some other constant term. So for now, I'm just taking all the constant term to the right hand side and just saying it is equal to some constant. I won't bother too much about the value of that constant right now. Okay. So this is what that equation looks like. And so now you see that this looks like the equation of some circle, except for in what condition it is not going to be a circle.
When
this-
sigma alpha I is equal to
Yeah.
0.
Correct. So we have to make two cases. Case one, what if sigma alpha is equal to 0? In that case, you will see that these first two terms are going to go away, and you are going to be left with simply something times x plus something times y is equal to constant, which is a line, right? Again, you have to be careful. There could be cases where these coefficients themselves are 0, and then you may get some special cases. So I'll leave this as an exercise for you to fully solve that. What are the cases, the sub cases within this case? But if you look at case 2, when sigma alpha I is non-zero, okay. So if the sigma alpha is non-zero, then this certainly looks like a circle. One more thing we can do in this case, suppose sigma alpha is non-zero, we can simply divide our whole equation by sigma alpha I. Okay, so if I go back to my original equation, this one, right? Alpha 1 p gamma 1 plus alpha 2 p gamma 2, so etc. So what if I consider a new equation where I've just divided both LHS and RHS by the sigma? So like that. Is equal to, and I have to divide the RHS also by the same term. So what I'm saying is that think of these coefficients as the new alpha I, right? Now we will see that the sum of these green brackets is now 1 actually. So what I'm saying is that without loss of generality, so this is a very important phrase, WLOG, which means without loss of generality. What that means is that it allows me to make some simplification of the problem, but still we are fully equivalent to the original problem. So here I'm we can assume that sigma alpha I is equal to 1. The reason why we can assume that is that if I solve this problem where this condition is assumed, from that I can directly get the original problem also. Because multiplying or dividing the whole equation by any non-zero constant is not going to make any difference. Okay, so that is the reason why we can make this assumption. Sigma alpha is equal to 1. Okay. And you see that this will make things easier for us because now in this equation, right, the x square and y square coefficients are going to go away. They are going to be simply 1, right? So I can directly write x square plus y square minus 2x, the same sigma alpha I hi minus 2y sigma alpha I ki is some constant. Right? So now can you tell me what is going to be the center? We already see that this is going to be a circle, but what is the center of that circle going to be? So to rephrase this equation as the equation of a circle, because traditionally we are familiar with the equation of circle as x minus something square plus y minus something square is equal to something like radius constant square. So how do we regroup this expression to make it look like that? So you see we can do something like completing the square. If I take the x square terms separately, then what term I need to add to make it a perfect square? So I can write it as x square minus 2x times this term sigma alpha I hi, right? Plus the square of this, right? And so obviously if I add something on the LHS, I have to add it to the RHS also. So the same term I'll also add to the RHS. But it's a constant, so it will sort of get absorbed in that constant term. And same can be done with the y square also. So that term will get added to this. So now you see I can rearrange this and write it as x minus this term. So sigma alpha I hi square plus y minus sigma alpha I ki square is some constant. And so in fact, that constant, if that constant turns out to be negative, then this locus does not exist. But if that constant is positive, then the square root of that constant is going to be the radius of that circle. And the center of that circle is going to be, so center is simply this, right? So the x coordinate is sigma alpha I hi and the y coordinate is alpha I ki. So the exercise for you to now to think is that, given that you have solved this most general problem, right? So this question 4, what values can you substitute for this alpha 1, alpha 2, hi, ki, so that you get each of the remaining subparts? So if everything we have done is correct, we should be able to obtain all the other special cases of this particular generalization. So the pattern which I'm following here, we would like to call this first generalize, then specialize. Okay, so first we generalize and solve the most general problem of that category. And then from there we specialize and substitute special values to see if we get anything interesting. For example, one very special case I would consider us to think about. Suppose I ask the question, find the locus of all points. So this is the question, find the locus of all points P such that, and given 4 circles. Okay, so given gamma 1, gamma 2, gamma 3 and gamma 4. Some 4 circles are given. And my expectation is simply the sum of all those is 0, for example, or some constant. So what can you say about this locus based on everything that you've done so far? Oh, sorry. Let me not even 4 circles. Let me just do with 3 circles first. What can I say about that locus? So in terms of this most general expression that we have found, what will the values of alpha 1, alpha 2, etc. be? If we compare this to the most general case that we have done here, so this most general expression, so this and the locus we are finding now, so what should the values of this alpha I be equal to?
So that all are ones.
They are all ones. Or if you want to normalize the sum to be equal to 1, then what can we say? Because we have put the without loss of generality, their sum is 1, right?
Then they are all 1/3.
1/3, right? So I could write this as 1/3 times P of gamma 1 plus 1/3 times P of gamma 2 is equal to 0. Okay, so all the coordinates of that center, if you see here, what do you think the coordinates look like? So what is that? Like x coordinate of that locus is going to be h1 plus h2 plus h3 by 3, and the y coordinate is going to be k1 plus k2 plus k3 by 3. So do you know what is this point?
Centroid of the
Yes.
O1, O2, O3.
Yes, correct. Okay, does everybody? I'm not sure if everybody knows this property, but the centroid where the medians are concurrent, that point, the coordinates are just the average of the coordinates of the 3 points. So what we actually found is that, so if the centers of that circles are O1, O2, O3, then this locus will be a circle whose center is at that centroid. And the radius will be something. The radius depends on the value of the RHS and many other things. But so do you see that this sort of very nice special case emerges because we did this general problem. And do you see we can extend this just like a triangle has a centroid, any number of points you can consider a centroid. So even a quadrilateral has a centroid, even a pentagon has a centroid. And in every case, if we are talking about adding the powers with equal weightage, so this alpha 1, alpha 2 can be called the weights of the power. So if equal weightage is assigned to all the powers, then it is going to be a centroid. And if that weightage changes, so in general, maybe I'm talking about alpha times the first power plus beta times the second power plus gamma times the third power. So if this alpha, beta, gamma are not equal, then that point will change and maybe take some other position in the plane. So actually there is a very deep connection between this triple of the alpha, beta, gamma, the weights that we assign and the position of that point. And we are going to study this topic in much more detail later on. But if you're interested, you can read up about this called barycentric coordinates. Okay. And this is has a very deep connections to Sevas and Menelaus theorems, for example. Okay. But yeah, see, all of these possibilities can be developed if you think about the most general questions. So the important lesson here is that don't just solve one problem. Try to solve the most general version of that problem at the same time. Any doubts in what we did so far, or any part you want me to repeat? Okay. And also observe how we took what looked like a complicated problem, but broke it down step by step into something digestible. So at every step we are applying some problem solving tactic, which is going to be useful for you when you're doing problems. So that if I am presented with a what appears to be a very complicated expression, the first thing we can do is group terms together intelligently. So x square coefficients go together. Then we take suitable cases to consider when which terms are non-zero or zero. Then this is the most important step, that without loss of generality, we can divide the whole equation with some constant term, so that some particular goal, like for example, here the goal was sigma alpha is equal to 1. But maybe in some other question, we want sigma alpha s square to be 1, or some normalization like that is required. And then finally regrouping the final expression so that it starts to look again like the equation of a circle. So, adding the term to complete the square. So completing the square was involved here. So at each step, we are applying one small idea. And you never know that all the combinations of ideas we are studying, which one will be useful in which exam, in which problem. You cannot predict that. So you have to become, well versed with all these techniques, so that at any point you can quickly recall and apply the right technique. Okay. Okay, so if this part is fine, let us move on to the next section. So then we come to the radical axis part. I think we already kind of studied or explained a couple of things here, which I left at exercise for you. So first is that the fact that three radical axes, if you take or rather three circles, their pairwise radical axes are going to be concurrent. So that now we already understood. And now we also have, in fact, we have two constructions of the radical axis, right? Using the midpoints of the common tangents, as well as the what Jannavi explained, that we take a third circle which intersects the given two circles, and those pairwise radical axes can be used to construct that what you want. Any other construction that anybody can suggest? How do we construct the radical axis of two circles?
Sir, in the first locus problem, we had calculated values of O1t and O2t.
Yes.
So that is a constant. So we can
Yes, correct.
mark such t on O1, O2.
Yes, that is correct. So basically we had in the setup, it was like we wrote the equations of wherever that radical axis is going to intersect the line joining the centers. We had written the equations and computed that O1t is equal to, I think, R1 square minus R2 square plus t square upon 2d. Is that correct? Let me just confirm. I think this is the right expression. Okay. So we can compute this expression. That is what you are saying, right? We can compute this expression and find the location of point t based on that. Right? But which is correct. But one detail maybe I'd like to know, if everybody knows, that what do you mean by compute this expression? I mean, if I've given, let's say I've given the values, R1 is equal to 3, R2 is equal to 5, and whatever, then you can calculate and get this answer. But what if I have not given you the values of R1, R2? I've just given you line segment. That okay, this is the line segment whose length is R1. This is the line segment whose length is R2, and this is the line segment whose length is D. Then using these line segments, can you construct O1t now?
So we can calculate R1 square and R2 square, or those squares by BPT.
Okay, yeah. So I mean, that was I have to check that. Does everybody know those tricks? Okay, so I will not cover them here today. If you want, I'll have a separate video on that for anybody who wants to watch. But like how to construct or do calculations using straight edge and compass. Okay, so doing calculations using geometric tools.
We are not able to see the screen where you are right.
Sorry. Oh, sorry. Can you see now?
Yes.
Yeah. Okay. So calculating using geometric tools, that is the thing that we need to know, because then it doesn't matter what the values of R1 R2 D are, because they may not be nice real like rational numbers. There may be some irrational numbers or any other number like that. But whatever is the length of R1 and R2, for example, this is something very simple that you know that if I want to add two line segments, I can just place them side by side, right? I can draw them on the same line and I'll get the sum of their lengths. And same way for difference. But what about product, square root, division? So those things, I'm not sure if everybody knows about them. So try to find out the answers on your own, like how do you multiply two line segments, how to divide. But I will upload a separate video on that.
So we did this in
But yeah.
our standard 8 workshop at MPI.
Okay, you have already done this. Okay, that is fine. So then everybody knows these basic things. So you also know how to find square root in that?
Yes, sir.
Yes, sir.
Okay. So basically, if you know that, then you know that in this expression, O1T can be constructed using these R1, R2T, right? It's important to know that not every expression is constructible. Okay, so, like constructible means that given the input values, you can construct the output expression. So you can do square and square root, but famously, you may know you cannot compute cube root, right? So at any point you have say, R is equal to cube root of X. Then even if you know the value of X, you cannot construct R always with the ruler and compass. So there are exceptions to when this can or cannot be applied, but square root, addition, subtraction, all that can be constructed. Okay, yes, but this is a good solution for constructing the radical axis. Okay. Any other solutions? Okay. If not, then moving to the next section. So the angle of intersection. So as I already explained in the video, that angle of intersection can be defined for not just two circles, but any two curves which intersect each other. And that the point at where they intersect, if you draw the tangents, then the angle of between those tangents is what we call the angle of intersection. So in particular for circles, one special case that we considered was orthogonal circles. And orthogonal circles actually, they have some very useful properties related to coaxial circles, which we will study later on also. But again, just to refresh the basic like characterization of two orthogonal circles. So what I had observed in the video was that the raw definition is that the tangents have to be perpendicular to each other. But taking that as a starting point, the consequence is that because the tangent also passes through the opposite center. So in fact, what we have is the fact that the distance over O2 square is equal to R1 square plus R2 square. And this is a necessary and sufficient condition to say that two circles are orthogonal, right? So I hope you followed that part, everybody. And I mean, we can really use this in many different places to solve problems. Actually, one question which you already did earlier today, in which this was kind of implied. Given one circle, so suppose this black circle is fixed, and I want you to think about all the circles which are orthogonal to the black circle. What does that set look like?
So
See
we
that we
given the black.
We are just given the black circle, and you have to find all the circles which are orthogonal to the black circle. Yes, Aditya.
So then construct a circle with center O1 and radius O1 O2 square.
Oh no, I'm allowing you to choose O2 anywhere. So we don't know O2 square.
Yeah.
O1 O2 square. So we have a lot of freedom.
We don't know R2.
We don't know R2 also.
Okay.
Yes, but you're right. Suppose I know R2, then I know R1 square plus R2 square. So then I know this quantity. So then I know where to locate that circle. But I'm saying you're free to choose R2 also. So what is that family of circles going to look like?
It will be the coaxial circles like the earlier problem.
Yes, correct. Do you see that? It's going to be the coaxial family, because suppose I choose that this point is the point of intersection of my given circle and the other orthogonal circles. So then I want a circle which is tangent to this line at that very same point, right? So I want a circle which looks like this, like this, like this. So in fact, you see that this is exactly the family of all circles for which the power of O1 with respect to that circle is given by distance of this one square. So you see there is one more way to characterize two orthogonal circles that, so if O1, so O1 comma R1 is what I'm using a shorthand to denote the circle which has center O1 and radius R1, and O2 and R2. So this is the second circle, are orthogonal. It also means that the power of O1 with respect to the second circle is equal to R1 square. And power of O2, the center of the second circle with respect to the first circle, is R2 square. Because those are the square of the tangents, right? The tangent between the two, the length of that tangent square is the power, right? So therefore, this length is R1 and this length is R2. So therefore, the power of O1 with respect to the second circle is R1 square and vice versa. And because of this property, this is the connection between that previous problem that we had done, question 4, and the orthogonality over here. So the fact, so if I can go back to that previous problem and rephrase the solution as, so this one, right? So I can characterize these green circles as, they are actually all the circles which are orthogonal to this particular circle. So with center P and radius root K. So if I consider this as my reference circle, then all these green circles are orthogonal to my reference circle. Okay, I hope this point is clear. So yeah, orthogonality has very deep roots with other aspects of the power of a point theory, actually. Okay, so keep in mind all these multiple ways to characterize orthogonality. You don't know which one will be useful when. Just as in other geometry, you know multiple ways to define, like for example, isosceles triangle. You know multiple ways to characterize an isosceles triangle. Like one condition is that two sides are equal. Another condition is that two base angles are equal. Another condition is that the perpendicular bisector of the base passes through the vertex, and so on and so forth. You know many characterizations. Some two altitudes are equal, two medians are equal. All these are equivalent characterizations of a triangle being isosceles. In the same way, all these are equivalent characterizations of two circles being orthogonal. And so each characterization has some utility given, whatever conditions are given to you in the problem. So keep all of those in mind and try to keep add to this list. So as many more characterizations that you can come up with, the more useful it may be as a problem solving tool for you. Okay, so then coming to the problems in the orthogonal section. So I actually forgot which of these I already discussed in the video, but just quickly to go over them. So the first question, right, where I'm considering I think I discussed the first question if I remember, right?
Yes, sir.
Yes. So I have two circles and I'm considering the radical axis, right? So let us say gamma 1 and gamma 2 are my circles and the radical axis L. And if I take any circle whose center is on this radical axis, not have any relation with these two circles. But suppose I'm given that there is a circle such that, so given that this circle gamma is orthogonal to gamma 1, omega is orthogonal to gamma 1, then what we are asked to prove is that this implies omega is orthogonal to the second circle. And in fact, this is an if and only state. So any circle with a center on this L is either orthogonal to both the black circles or orthogonal to none of them. So this was what we had proved. And I think the proof was fairly straightforward. I hope you are able to follow. And you see again, it goes back to the fact that the power of this point is equal with respect to both the black circles, which means that the length of the tangent, so that that tangency interpretation keeps coming back again and again. That the length of these tangents being equal is the reason why this circle is orthogonal to both of them. I don't know. Are there any other proofs of this property that may be worth discussing? Because I could not come up with anything else. Yeah, I don't remember. But I had also encouraged in the video to for you to think about the sort of the converse statement that suppose I'm given that there is a circle which is orthogonal to the two black circles. Can we conclude that its center has to lie on the radical axis? So has anybody able to do that exercise? So now what is given is, I don't know where the center of this circle is. Okay. But what is given to me is that that circle is orthogonal to gamma 1 and omega is also orthogonal to gamma 2. Then my claim is that the center of gamma lies on the radical axis of gamma 1 and gamma 2. So if I call that radical axis L. But do you see why this also has to be true?
Yes, sir.
Yes.
We can
Because
show.
again, yes, go ahead.
Yes, sir. We can show that the power of the point, power of the center of the circle with respect to both circles will be equal.
Yeah, correct. Because of again, orthogonality implies that power of O with respect to the first circle is this radius square, and the power of O with respect to second circle is also radius square. So therefore, O has the same power with respect to both circles, so it has to lie on the radical axis. Okay, is this argument clear? So you see, in fact, there are three statements over here where any two of them are true, the third is implied. So the statement 1, statement 2, and statement 3. So if a circle is orthogonal to two circles, the center lies on the radical axis. If the circle center lies on the radical axis and one orthogonality is given, then the other orthogonality also follows. Okay, so these three statements are like interrelated in that way. Okay, then question 4. Sorry, not question 4, question 2 and question 3. So these construction, that how do we construct a circle which satisfies some given properties? And in fact, there is a whole family of circle construction problems that we may do at some point, where some three pieces of information and you have to construct the circle using that. So like the most basic problem of that kind you may know is that suppose I give you 3 points, point P1, P2, and P3. Then construct a circle passing through all the 3 points, which is obviously the circumcircle, right? And suppose I give you 3 lines and construct a circle which is tangent to all the 3 lines. Then we again know the in circle and the X circles, right? In the same way, the idea is that point and line are actually both examples of circles only. A point is a circle with 0 radius, and a line in some sense like a circle of infinite radius, because if you know keeps increasing the radius of a circle, it starts to look more and more like a straight line. So in fact, both of these are special cases of the most general problem where I've given any 3 circles in the plane and now construct a circle which is tangent to all 3 circles. Okay, so this is actually a famous problem. I believe it is called Apollonius problem. So this is the most general case where I'm given 3 circles. But you can imagine all permutations of combinations, that point, line, and circle. These 3 objects can be combined in various ways, like 3 points, 3 lines, maybe 2 points and 1 line, 2 points and 1 circle, and so on and so forth. So in total, we actually get 10 such variations of the problems, and we can study all of them together. So we are going to do that topic at some point. But this question 2 is somewhat in a similar context. That is that I'm giving you 3 pieces of information. So like question 2, I believe, is that we are given a line, a point, and a circle. Okay, so we are given a circle gamma, a line, and a point. Okay, so we want to construct a circle which passes through P, is orthogonal to gamma, and whose center lies on L. Okay. So construct a circle omega such that center lies on L, passes through P, and orthogonal to gamma. So how can we construct this circle? Using ruler and compass, obviously.
Sir, can I tell?
Yes, Nandini.
Yes, sir. Can you name the center of the given circle?
Okay.
Yes, and let's construct the required circle in the auxiliary figure.
Okay. So we want the circle which is passing through P. Maybe center, maybe somewhere over here. Suppose this is the desired circle. Okay, and let its center be C. Okay.
Yes, so we know that CO square minus R square is equal to CP square.
Is R the radius of the given circle or the
Yes,
auxiliary?
given circle.
Okay. So CO square minus R square is equal to CP square, correct?
So we can write R in terms of CO square and CP square.
Okay.
Then we can drop a perpendicular from C to OP.
Okay.
So we can write CO square minus CP square as OD square minus PD square.
Yes, correct. By the same trick that we used in the radical axis proof, you can write
Yes.
this is going to be OD square minus PD square. Okay.
And we can substitute OD is equal to OP minus PD.
Yes, correct. So when we expand, PD square will cancel and we'll get OP square minus 2 times OP into PD. Okay.
Yes, so we will get a PD in terms of everything constant.
Okay, so this was R square. So R is constant, OP is also constant. Yeah, so in this equation, the only variable is PD, right? And everything else we know. So we can compute PD, and so we know the position of point D, and then from there we can draw the perpendicular and we'll get the point C. Okay, I hope everybody understood the approach that given the fact that, so we use multiple things over here. The first is the orthogonality gives us this condition. Then we want to eliminate things from point C and bring them onto line OP, because line OP we know understand very well. And so therefore with the substitution and some simplification, we are getting an expression which has only the line segment PD in it, which we can compute. And therefore we know we can find the position of point D and finish the problem. So Nandini, your solution is correct, but actually you can simplify your approach by through some observation that what we are doing here, does it remind you of something? As you said, what was this trick involved? That from OC square we came to OD square. This trick we saw in the radical axis proof, right?
Yes.
So don't you think it is curious that the same trick is applicable here also? And could there be some reason why the same trick is applicable here also? So tell me, what is the power of the point D with respect to the given circle? If I just write it to one side, the power of the point D with respect to the given circle. If I call that given circle gamma, it will be OD square minus R square, correct? And if you look at this part, when we computed R square is equal to OD square minus PD square. So how much is this OD square minus R square also equal to?
So power of point D with respect to the given circle will be PD square.
PD square, correct? But what is PD square? Can you give a different name to the expression PD square? Can I think of PD square as the power of point D with respect to a circle of 0 radius centered at point P? So this idea of a circle of 0 radius may be somewhat strange, but just think about it. A circle at point P of radius 0. Wouldn't the power of D with respect to that circle be dp square? So what I'm actually saying is that the point D has equal power with respect to this 0 circle and my given circle.
As in, so we can say that PD would be OT1.
PD equal to, sorry, can you repeat that?
So that OT1, like the rat is like C.
Yeah,
radical.
exactly. This point D is exactly that point T that we had computed earlier. Nothing different. So let me, yes, go ahead.
So we can construct the radical axis of the given circle and P.
Yes, that point circle at P, correct. And that radical axis is exactly this green line which you have drawn, CD. Okay, does that make sense? Let me just state everything again. And you know, the funny thing is this, I had done the same problem last year or the year before that when I did PowerPoint topic. And I had a different proof of this, completely different approach to solve this problem. And when I completed that approach at the last step, I realized, oh, this was such a simple approach that I can do now. And you know, that has created a sort of myopia that now I can only see the simple approach. Now I have to struggle and remember what was that difficult approach I had done earlier. So I don't quickly remember that difficult approach right now, but maybe if I can go back and watch the previous meeting, maybe because there is one more solution to this question, which is more complicated. So I mean, has maybe less value because it is more complicated. But so this is how we can think about this problem. In fact, you don't forget the line given. I want a circle which is orthogonal to my given circle and passes through the point P. Okay, so this is the circle I want. Okay, this is the auxiliary circle which I want. So what is given to me that this omega is orthogonal to gamma and omega passes through P. And so now this is where we have to realize that actually this condition that omega passes through P can be completely replaced by the condition that omega is orthogonal to that circle of center P and radius 0. So orthogonality with respect to a circle of radius 0 is just saying that that circle passes through that point. So we have exactly the same situation which we discussed just few minutes ago, that I'm given that there is a circle omega which is orthogonal to two circles. And so what can we conclude? Therefore, the center of omega lies on the radical axis of these two circles. So the two circles under consideration are the gamma circle and this P0 circle with center P and radius 0. So imagine we are considering the radical axis of a point and a circle, not two circles. Okay. So it makes sense to talk about the radical axis of this point and the circle. The locus of all points which have equal power with respect to this circle gamma and this point P. Because when I'm saying point P, implicit is there is a circle of radius 0. And so if I construct that radical axis will have this center of gamma. And then wherever that radical axis intersects that given line L, so that line L which was given, and the radical axis, wherever they intersect, that is going to be the center of their desired circle. Understood? Follow on question. How do we construct this radical axis of a point and a circle? So again, focusing on just that part. So this is my given circle, and this is the point of 0 radius. How do I quickly construct this radical axis which I'm looking for? And if you think about it, in this case, that previous approach we had done where, we draw one new circle passing through two given circles. I don't know whether that would be very useful. So think back to the very first construction of radical axis which somebody had suggested in today's lecture.
So we'll draw tangent from point P to circle gamma, and then we
Yes,
will join midpoints.
correct. So I'll just draw the tangents and I'll take the midpoint. And so the line joining the midpoints is the radical axis of this circle and this point. And so now wherever this line intersects that other given line L, that is going to be my center C.
Or so we
So
could
do you-
join OP and we get the point D.
Okay. Yes, we can also find the position of the point D, either through computation or we can some other approach. But do you see that how by continue to analyze the problem even after it is over? Now, just if I were to ask you number of steps required to solve the problem, we have reduced to considerate now, right? Now we just find the common and just draw the tangents from the point to the circle, take the midpoint, join them wherever that intersects the given line. We have found the center. So this repeated simplification gives you very new ideas, and this whole perspective of thinking of every point as a circle of radius 0. You'll start to see this more and more in various places, that how this can be very useful. Okay. So yeah, so every approach has something new to teach us. So assimilate all the details as much as you can. And continue. Maybe there are more approaches also. As I said, there is one very difficult solution which I have forgotten, but maybe you can find it with some effort. Okay, so this was question 2. What about question 3?
Sir, question
And
3
all
can TKP to question 2.
question 3 can be TKP to question 2. Okay, interesting. Let me think about it. Circle gamma line. Actually, I think you are correct, but I also have to work out the details. So what is given now is a circle, a line, and a point P. And this time let me take the point P on this side. We have to construct a circle omega. So we are interested in construct circle omega such that. So first is that point P lies on that omega. Then L is the radical axis of that given circle and the circle to be constructed. Janvi, can you explain how you are able to formulate this
sir.
problem as a TKP?
We can choose any point on L, say Q.
Okay.
And then, sir, can you share the screen?
Oh, sorry. Yeah.
Then we can draw QR tangent to the given circle.
Okay.
And circle with center Q and radius QR. So
Okay.
we get that this
Draw
circle
this
is
circle.
orthogonal to the given circle.
Yes, correct.
And since this circle lies on the center of the circle lies on the radical axis of gamma and the desired circle, we get that this
Yes.
circle is orthogonal to the desired circle too.
Yes, correct.
So then now we can follow the procedure.
Yes, correct. Yes, understood. Correct. Okay, let me just draw it again in the correct order. So if I consider let this be the auxiliary circle which we are interested to compute. So this is the circle which passes through point P, and this L is given to be the radical axis of gamma and omega. So what Janavi explained, let us take any other circle centered on this line L, and from there we construct a circle orthogonal to my given circle gamma. Okay, so this is that any orthogonal circle, right? Not any actually, because already sorry. Very good. Okay, so Q is construct this circle, if I call it gamma 2. Gamma 2 is a circle constructed such that it is orthogonal to the given circle. And the center also lies on the radical axis of gamma and omega. So using the previous theorem, it implies that this circle gamma 2 is also orthogonal to my omega. And so now, again, if you look at all the constraints that omega has to satisfy, so omega has to pass through point P. So the point P has to lie on omega. This is the first condition that needs to be satisfied. Then omega also has to be orthogonal to gamma 2. But we need one more. What is that line L on which the
That
center of
line
gamma?
is the perpendicular from the center of the
Yes.
first circle to line a given line.
Yes, correct. Because we know the radical axis is perpendicular to the line joining centers, right? So we can flip that and say that if I draw the so not supposed to land here, but luckily it has. Let me just take it to one side. So it doesn't look perpendicular, but I mean, if I take the perpendicular line from the center to my L, then I know that the center of gamma has to lie on this line also. So I have additional condition that the center of gamma has to lie on this line L2, if I call it. So all the conditions of the previous problem 2 are satisfied over here. So we can construct that using that approach. Okay, does everybody follow this? We could simplify the diagram somewhat, because this center Q and this blue circle has been chosen arbitrarily here. Just to save some steps, what we can do, can we think of choosing the point Q over here only? Because anyway, we have to construct this perpendicular line, right? So just to save us some steps, it doesn't really change anything. It's the same approach, but so I mean, the actual steps to be followed to be something like this: that this line L is given, this point P is given. So first step is we construct a perpendicular line, and now this is the point from where we want to draw that orthogonal circle. And so can just draw the tangent from this point to this circle, and so that will mark the radius of my that middle circle. And then after that we can do TKP. Okay. Yeah, any other approaches that can also be tried? I vaguely remember that even question 3 has some alternative ideas, but right now I'm not able to figure them out. Maybe if I can locate those alternative proofs, we can discuss them next time. But you also give it some thought that what other ideas which we have studied so far can be utilized to solve question 3. Okay. I mean, instead of doing a TKP to question 2, is there a way to directly solve question 3? That is something worth exploring. I think. Okay, but anyway, we'll leave that aside for exploration. So question 4, this given two fixed circles. So this configuration, let me start talking about this in more detail, because as we are approaching the next topic, which is coaxial circles, right? So again, I'll send you a video to watch sometime mid this week, where we'll discuss the coaxial circle family in more detail. But just to illustrate the idea with some initial setup, so that you can start exploring also before you have to watch the video. So actually we are going to use coordinate geometry to a good extent when we study coaxial circles, and that is for a good reason. It is not because many of those things can be done using pure geometry also. It's not that it cannot be done, but coordinate geometry will provide a better frame of reference as to the symmetry of the situation, that how, because we are going to consider two coaxial families of circles. So the fact that the x and y coordinates flip in those cases is very useful to consider. Okay. So these circles, the two circles which I talking about, right? Gamma 1 and gamma 2. Let me just draw them. So this is my circle gamma 1. And roughly let me take the circle gamma 2 here. Okay. And I've sort of set things in such a way that this line in between is the radical axis of gamma 1 and gamma 2. Roughly speaking, it looks like that. And so what I'm going to do is this line, on this line, if I take any point, now you already studied this multiple times, that I can consider the circle centered at this point, which is orthogonal to both the circles simultaneously. So maybe that circle is something like this. Okay. And what the question asks us to prove is that, so the point at which this blue circle is cutting our horizontal line, so this circle itself will vary. So as this point O changes, but these points don't change. That is the claim. So if I call these points A and B, the position of A and B is fixed, even as this blue circle varies. That is the claim being made. And actually, let me redraw the diagram, because this is kind of misleading. I know by hindsight, because the topic we are going to do next, how this circle is going to look like. So let me just make one correction over here. In fact, the redrawing of the diagram is a kind of a hint for you that about things which are going to happen in the next lecture. So this point A and B, the claim is that as the center changes, center and the circle changes, the points A and B don't change. So firstly, has anybody already showed this result?
Sir, we can do it without coordinate geometry too.
Yeah, we can do it without coordinate geometry. That is correct. So how do we start?
Can you name the point of intersection of the horizontal and vertical line?
This point. Okay.
So let O1T be K1 and O2T be K2.
Okay.
So and let O1 O3 O1O be D1 and O2O be D2.
Okay. So this is D and D2. So can we call them D1 and D2 just for symmetry?
Yes.
Yeah. Okay.
So we by Pythagoras theorem, we know that AT square is AO square minus OT square.
Yes.
So it is equal to R3 square minus bracket D square minus K1 square.
So you're calling the radius of this as R3, right?
Yes.
Yes.
And so we know that D1 square is R1 square plus R3 square.
Yes, because of the orthogonality.
Yes.
D1 square, which is distance of O from O1, will be equal to R1 square plus R3 square minus K1 square. Yes.
So
And
we
so
get,
R3 square will cancel and we get K1 square minus R1 square.
and that is a fixed value. So
Yes,
A is fixed.
correct. And similarly, have you computed BT also?
Yes, it is K2 square minus R2 square.
Okay. And what else?
We have to prove that A and B are fixed points. So
Yes, yes. No,
and
yeah, we have completed the proof, but is there anything else that we can observe over here? What can you say about these expressions themselves?
Sir, AT is equal to BT.
Yes, because if you think about it, this 80 square, this is the power of t with respect to the first circle, and this is the power of t with respect to the second circle. And knowing that t lies on the radical axis, so we can say these are also equal. So in fact, not only a and b are constant, the midpoint happens to be the point t. Okay. Okay. So does everybody follow this approach? What the calculation we have seen here?
So that would like do that imply K1, K2 is equal to, or maybe not.
No. Okay, but yeah, but this is a perfectly fine way to do this problem. And it has very important implications because we have already seen the interpretation that we can treat points as circles with zero radius. So here, in a way, I encourage you to think about this offline and realize that what I'm also saying is that, so if I call this circle, this blue circle as gamma, so we already know that gamma is orthogonal to gamma, omega. Omega is orthogonal to gamma 1, omega is orthogonal to gamma 2. But because it passes through points A and B, omega is also orthogonal to the zero circle at A and the zero circle at B. Okay. And in fact, every circle of this family, this blue circle, the blue circle family is going to have the same properties, all these in fact. And I mean, just to illustrate this, suppose so if I call this circle omega 1, because this is just one candidate, right? If I can choose a different color and draw a slightly different candidate of the same family. So maybe another circle, change the color, change something. So here is one more circle of the same family passing through A and B. And all these four will be true for this new circle also, gamma 2. So both gamma 1 and gamma 2 satisfy the same four conditions. So what you start to realize, in fact, I'm going to get two sets of circles. So let me call the omega family, which is this blue and purple circles, and the gamma family. Okay. And the interesting thing you'll observe is that you can take any circle of the omega family and any circle of the gamma family, and they will be orthogonal to each other. So far this second family has only four candidates that we found. So these two black circles which are given and points A and B. So your sort of homework is to discover what are the other members of this gamma family. Already the omega family, the purple family is well established. They are all the circles passing through A and B, right? You can take any circle passing through A and B, that will be a candidate of this purple family. But this black family is still somewhat a mystery to us. What are the circles of this black family? So that is your task to discover. And I think we already sort of done the groundwork of this today, that you know many properties which you can apply now to do this. So I really encourage you to try and do these things on your own as much as possible, so that it gives you a chance to develop the theory in your own terms. That will also help you to remember it better. Instead of me telling the proof, if you have found it, it improves the probability that you recall the ideas very quickly in exam. Okay. So I think that pretty much concludes what I wanted to discuss today. There are also some problems based on power of a point, which, like, if I look at past few RMO papers or INMO papers, there are a few questions where we have prominently used power of point in at least one of the solutions. So I'm still gathering those questions. I'm not finished doing that, but once I do that, I will share that as a separate PDF with you, so that you get some practice actually solving contest problems also using these ideas. But note that I've never done this before, because generally speaking, I believe that sorting out the problem, that these are the 5 problems using power of a point, that is a luxury that you have right now, but you will not have that luxury in exam, right? The exam paper will not tell you that this question is going to be done with power of a point. So discovering the fact that a given problem can be done using power of a point, or any trick for that matter, is part of what you need to learn. So even though we may share a few problems like that, know that I'm sort of giving you half the battle without any effort, that I'm telling you that solve this problem using power of a point. Eventually, when you have multiple such tools, so many configurations, so many theorems, which property to apply where is important part of your experience, which you need to develop. Okay, so actually we are done a bit early, so don't have anything else to share right now. So we can stop early also, or if anything else that you want to bring to my attention, we can discuss right now.
Sir, can you solve 11th question from selection paper?
11th, I already did that in the last class, actually, if you remember. Oh, I left it halfway. You want me to complete it from that point? We can do that. So the 11th question was that when you have the equation, right, m square is equal to, let me just pull up the paper. So question 11. So I had started to solve this question last time. Not sure if you remember the partial proof that we did. So basically 2m square is equal to 3n square minus 1. And so we are given that m and n, if a particular pair of integers satisfies this equation, then we also expect that this am plus bm and cm plus dn, this pair also will satisfy the same equation. So if we substitute and expand the terms, I'm saying 2 times am plus bn square is equal to 3 times cm plus dn square minus 1. And from here we had simplified and basically got rid of few terms. So in particular the middle term, right, am bn and cm dn, that gets cancelled because of this given property. So because of this property, that middle term can get cancelled, and regrouping, and in fact we can equate the -1 part from here to here. And so if I do all of those things quickly in one step, and just correct me if I make any mistake, but hopefully I'll do it right. So I get directly to a square minus 3c square minus 2 is equal to n square times 2b square minus 3d square. I'm forgetting the last term. Can anybody remind me what is the last term over here?
So minus 3.
Minus 3. Oh, yes, it will be the coefficient coming from. Okay. So we had reached this point, and now here we have to say something about under what conditions will this equation be true. Importantly, this equation has to be true for every pair of m and n which satisfies my given set of solutions. And so if I'm being told that ABCD are constants, so if I call this term as capital L and this term as capital R, so I'm saying L times M square is equal to R times N square, where L and R are constants, but M and N may vary. So for different values of M and N, the ratio of L and R will change. So for example, sorry, last time I was struggling to find a sample solution of this, but
So you
trust me,
can
there are
take
solutions.
11 and 9.
So
11 and
11
9.
and 9. Okay, so M is equal to 11, N is equal to 9. And one more solution,
Just 1 1.
1 and 1, right? 1 and 1. So you see, these are two different solutions where the ratio of M and N are different. And so if L and L are non-zero, you see this leads to contradiction, because in one case the ratio L upon R will be like 11 square upon 9 square, and in another case the ratio will be 1 upon 1. So the only way to avoid the contradiction is that both sides of an equation have to be 0 at all times. So it forces that LHS is 0 and RHS is 0. Okay, so what is forced is that this is 0, 2a square minus 3c square minus 2 is 0, and 2b square minus 3d square minus 3 is also 0. So whatever ABCD you choose, they have to satisfy these conditions along with that given condition. 2ab is equal to 3cd. So in general, there could be multiple possible values of ABCD which satisfy this system of equations. But the question asks that we have to find the value, the combination where the sum of A plus B plus C plus D is the smallest. So at that point, you can either do some trial and error, or actually you can analyze this systematically even further. And actually, I think it turns out that, let me see. I believe you get something like A and D have to be equal, something like that, if I remember correctly. Okay. So why don't we all try to analyze this from this point? So one way to proceed when you have information like this, like 2a equal to 3cd, which tells us something about divisibility, right? The fact that some term on the LHS is divisible by 3 and some term on the RHS is divisible by 2. So we have some information about, so now which one do we choose as 2 and which one do we choose as 3? So if you look at this equation, look at the the first equation. I can rewrite that as 2a square minus 2 is equal to 3c square. So do you see that the LHS is divisible by 2? So 2 divides the RHS and 2 cannot divide 3. So therefore 2 divides c square. In other words, c is E1. So c will be 2 times C1 for some integer C1. And similarly from the second equation, do you see that basically 3 divides all the terms except 2b square, right? So therefore 3 has to divide 2b square. And so I can write b is some 3 times b1. Okay, so this important substitution that c is 2 times c1 and b is 3 times b1. So I can replace all occurrences of b and c with these new terms. Okay, so if I do that, my entire system will get rewritten into a new equation. So first thing you'll observe is that because b will be replaced by 3b1, so this 2 and 3 will get cancelled. And so what will be left with is actually a times b1 is equal to c times c1 times b. Okay, so this is what if the condition 0 gives us this one. And then how do you rewrite condition 1 now? 2a square minus, so instead of 3c square, I should write 12c1 square minus 2 is equal to 0. And cancelling one copy of 2, this means that a square minus 6c1 square minus 1 is equal to 0. And from the second equation, very similarly, I can replace the first term by 18b1 square minus 3b square minus 3 is equal to 0. And so again, cancelling a copy of 3, I'll get 6b1 square minus b square minus 1 is equal to 0.
Sir, I think in second equation, it's 3d d square minus 2b square.
Yes.
Oh, okay. It should be 3d square minus 2b square. Okay, yeah, because I'm taking n square to the other side, so the sign will not change. Yeah, thank you. So everywhere the signs will be reversed. But I think that doesn't change the validity of the divisibility argument, right? Still, we have that 3 divides 2b square. So this equation will be minus plus. Okay, so this is your new set of equations. AB1 equal to C1D and these two equations. Okay. So how do we continue to simplify this further? And by the way, important thing to note, I'm just doing this as an academic exercise. But as far as solving the question which was asked, we just want to find the smallest values of ABCD, right? To satisfy this. So at some point, you can start doing trial and errors with the most smallest values you can imagine. So you can try like A is equal to 1, B is equal to 1, and no, start doing basic trial and error 1, 2, 3, 4. I think the actual solution turns out to be A is equal to.
So first of all, I think trial and error, we can use congruence, right?
So we already done to some extent we have used divisibility to simplify the question. Yeah, you're right. We can do congruences also. That will also help us actually. Because for example, if you look at the first equation over here, this a square, if I write this as a square minus 1 is equal to 6 times c1 square. So this puts some restriction on what values of a can be chosen, right? It has to be a square minus 1 has to be multiple of 6. So we can use that somehow to reduce the trial and error also. But I'm just continuing to think if we can analyze this further in some way.
Sir, from equation 1 and 2, we get 6 divides a square minus d square.
Yes, 6 divides a square minus d square, right? Or d square minus a square, either of them. Because if I add the two equations or either subtract one from the other, this minus 1 will get cancelled. No, I'm actually trying to think of something very different altogether. See, I want to leverage this information. This AB1 equal to C1D is very important information to connect the terms together. So the approach I'm thinking is, see, these look like middle terms, right? Of a something square plus something square. These AB1 and C1D are going to become middle terms of that something square. So I'm just trying to figure out what those expressions are, for which this AB1 and C1D will come naturally as the middle terms. So for example, let us consider a. So you see, actually I can consider a plus any constant times b1 square, and same k over here also. So if I expand, I'm not equating these two, but if I just expand this individually, on the LHS, I'll get a square plus k square b1 square plus a 2ak b1. And here I'll get c1 square plus k square d square plus 2k c1d. So do you see that these middle terms are going to be equal because of this given information? Because a1b and ab1 and c1d are equal. So how can we leverage this in some intelligent way?
Sir, if we subtract 2 from 1, equation 2 from 1.
Okay, yes,
Then
correct.
we get a square plus 6b1 square and minus
Yes,
and common 6c1 square plus d1 square and
right,
equal to
correct,
0. And then
correct.
we will add and subtract 2 root 6 times ab1 and which is
Yes,
also equal to c1d.
yes, correct,
They will
exactly.
complete the squares and then we'll get a plus root 6 b1 square is equal to root
Yes,
6 c plus d1 square, d square.
yes, correct. And then we can get rid of the square roots, or we can do something after that.
Yes, sir.
Okay, so is everybody following the idea which Om is suggesting? So we can reach there from here also. So let us say I write this first term minus the second term, right? So a plus kb1 square. I don't know what value of k I want to choose right now, but let me just write it in general terms. So a plus kb1 square minus c1 plus kt square. If I expand it, this I'll get to get this, right? This first whole expansion minus the second expansion. And then out of that, already these middle terms are going to get cancelled. And so I will get a square minus c1 square plus k square times b1 square minus d square. And from here, looking at this equation 1 and 2, it gives me the inspiration that maybe k should be root 6, because if k is root 6, then this k square will become 6. Okay, so if I put k is equal to root 6, I'm going to get a plus root 6 b1 square minus c1 plus root 6 d square. I'm just rewriting the first line of my equation, is equal to this a square minus c1 square plus 6 times b1 square minus d square. And now this is equal to 0, correct? Because of if I subtract 1 and 2, 1 from 2 or 2 from 1, you'll see that is exactly equal to this one. And so what I'm able to conclude is that a plus root 6 b1 square is equal to c plus root 6 d, c1 plus root 6 d square. And so eliminating the squares, I get a plus root 6 b1 has to be equal to plus or minus c1 plus root 6d. And if you already know something about how, assuming that this ABCD are all non-zero, then a given expression cannot be written in two different ways of the form, like all the integers of the form x plus root 6y. There is only a unique way to represent any assert in this way, right? So this is a separate exercise for you to prove that. Suppose if x1 plus root 6y1 equals x2 plus root 6y2, then prove that actually x1 and x2 and y1 and y2 have to be equal. This is forced from this equation, assuming that all x, I, y are non-zero, belong to natural numbers, for example. Okay, so this is an exercise for you to prove later on. But you see that this implies directly that a and c1 are equal and b1 and d are equal. And from there you can further make it easier to do the trial and error, because now we don't have 4 variables, we have only 2 variables, because the other 2 variables are going to be equal to the first 2 variables. Okay, so this is the outline of the approach that you can take. Obviously, this may look like a lot of things to do in the exam time, because this was what I think 5-mark question, so you had 9 minutes to do all of this. So I understand that this looks like too much to be done in 9 minutes, but that was the ideal. I'm not saying that that is what you have to achieve necessarily. If you can do that, that will be very good. See how much you can simplify the calculation. Of course, explaining takes more time. Doing these calculations quickly one after the other will take less time for you. So it's a useful skill for you to develop, not just for PRMO, but paper like JE, really a question like this has to be done in 9 minutes. There is no alternative. So you have to develop your speed for that anyways. Okay, I think we're almost out of time. So so we'll continue next time. I'll again send a video for you to watch for coaxial circles, but it will take me 2-3 days. So use that time to develop the coaxial theory on your own as much as possible, so that you've already done the background work when you watch the theory. Okay, that's all. Thank you. Bye.
Thanks, sir. Thank you, sir.
Thank you, sir.
Yes, sir.